I figured it was about 10 years ago that we started working on air sampling techniques and in particular passive air sampling technique. So I thought it was about time to sort of take stock and give a little bit of the overview of the work that we have been doing related to passive air sampling, and of course also some of the work that we're doing right now. Now, over these 10 years, of course, I have worked with a whole bunch of people, a lot of people in my research group at the University of Toronto, with my research associate, Ying Lei. The next group of people are graduate students that worked in one way or the other with passive air sampling. And what I present today will be mostly the work of Subhashini, Stephen, and Xianming. Then a number of undergraduate research students, postdoctoral fellows. And then we have a whole number of collaborations with people both in Canada and around the world. For a while we had funding from the United Nations Environmental Program, and that allowed us to work in Costa Rica, in Chile, and in Botswana. And more recently we have started a collaboration with some colleagues in Japan. But let's get started. So what is a passive air sampler? A passive air sampler is really just a sampling medium, and that may be polyurethane foam, or it may be an XAD resin that is placed in a shelter and then left in the environment for an extended period of time, during which that sampling medium takes up contaminants from the atmosphere by diffusion. And then you retrieve the sample, you extract it, and you get a number of the sequestered amount of a chemical, and you can interpret it in terms of air concentrations. Why would you want a passive air sampler? First of all, it's a very cheap device. You can build one of these things for less than $100 each. They're very small and light, so you can ship them around. And many of the studies that we have conducted, we just relied on the postal system, where we pack these things in a box and ship it out to people to put up in their backyard. And very importantly, they also don't require electricity. You don't need a pump because they take up the chemicals by diffusion. That's why we call them passive. And so because of that, you can use them also in areas where you don't have any electricity supply, like in very remote areas. Also in places where your electricity supply may be intermittent or unreliable. Now, the way we interpret these things, so what we do is we leave a sampler out for a certain amount of time, which we can call delta T, and at the end of which we extract the sampler and we quantify how much is in there, and so we get an amount in picograms or something like that. And as I said, it's a diffusion process, and like any other diffusion process, we can use Fick's law of diffusion to describe the uptake. So first of all, we need a concentration gradient. And so the concentration gradient driving that diffusion towards our sampler material is the gradient between the concentration in air and the concentration on the sorbent material. And of course, we need to convert the concentration in the sorbent material into a concentration in the gas phase by dividing it by an equilibrium sorption coefficient that relates the equilibrium distribution of a chemical between the sampling material and the gas phase. And we also need then a kinetic term. We call it a mass transfer coefficient K, which simply describes how fast chemicals get from the gas phase into our sampling material. And we need the area across which the diffusion occurs. Now, when we apply this technique to semi-volatile organic chemicals, what it means is that our sorbent air partition coefficient is a very large number. So in other words, our sorbent has a very high capacity for the chemical relative to the atmospheric gas phase. So what it means, our KSA is a very large number. If KSA is very large, this term here is very small, and we can simplify our equation where then our change of mass in our sampler over time is simply the product of the kinetic mass transfer term, the area, and our air concentration. And we can also sum up or combine the mass transfer coefficient with the area, and then we call this whole thing a sampling rate. And the sampling rate has then units of cubic meter per day. And essentially it expresses the volume of air that is being stripped of chemical in one day. So in a way it's comparable to a sampling rate that you would have in a traditional sampler, where you operate a pump and you collect a certain volume of air by drawing it through a sample material. And so a typical uptake curve would look something like this, that as a function of time, the amount sequestered in your sampler is increasing. And here the amount sequestered in the sample is normalized by the air concentration. But at one point, our sampler material will approach equilibrium. And in other words, where Cs over Ksa term will no longer be negligible. And if the sampler is left out long enough, eventually it will approach an equilibrium. And at that point, the delta M over Ca will approach the product of the Ksa, that sorption coefficient, and the volume of the sorbent material that we packed into our sampler. So from this we can learn that equilibration will occur faster for chemicals for which the sorptive capacity is small, in other words, where the Ksa is a relatively small number. And because that sorption coefficient is a very strong function of temperature, it also means this Ksa will be smaller at high temperature, and equilibration will occur faster at high temperature. Of course, the approach to equilibrium depends on how much sampling material you have. The more sampling material you have, the longer it will take for it to equilibrate. And but it's also not only important how much you pack into your sampler, but how much of that material is actually accessible to the atmosphere, and we'll get to that eventually. So in order to design and operate a passive air sampler, we need to know a number of things. So the first thing we should know is what is the uptake capacity of our sampler for the chemicals that we want to measure. So in other words, we need to know what that sorption coefficient between the sorbent material and the atmospheric gas phase is. And we would want to know that for different chemicals, for the chemicals that we may want to measure. We should know this number as a function of environmental conditions, for example, as a function of temperature or the relative humidity prevailing in the atmosphere. And we need to know it because it determines the length of the linear uptake region. So in other words, before our uptake curve tends to slope off and approach equilibrium. And therefore, we need to know our Ksa in order to determine how long we can actually use our sampler in the field. In addition, we need to know the kinetic term. We need to know that sampling rate. In other words, we need to know the slope of our initial linear uptake rate. And again, we would want to know that for different chemicals and for different environmental conditions. In particular, temperature and wind speed in this case are important. And again, we need to know it because it is that R value, that sampling rate, that allows us to convert the amount of chemical sequestered in our sampler in units of picograms into a volumetric air concentrations, picograms per cubic meter, that we are all familiar with and know as an air concentration. So what I want to do in this talk is take you through some of the things that we have been doing in order to characterize both the uptake capacity and the uptake kinetics of different passive air samplers. And eventually I also want to talk a little bit about what we can do with a passive air sampling system once we have properly characterized it and understand how it works. And I want to conclude then with telling you some of the work that we're doing right now. So let's start with talking about the uptake capacity of passive air samplers. Now, the particular passive air sampler that my group is working with, the most is based on XAD resin. So XAD is a divinyl benzene styrene copolymer. Really all you need to know, it's a white powder. And it's a powder that has a very high surface area. It has lots of micropores. And because of these micropores, it has a very large capacity for organic chemicals and therefore is suitable for passive sampling. In order now to measure sorption coefficients between the atmospheric gas phase and that XAD resin, we used a technique called inverse gas chromatography. Essentially what it involves is we put a little bit of the sorbent material in a very tiny gas chromatographic column, but not like the ones you know that are 30 or 40 meters long, but a column that is actually only a centimeter long. And then we inject chemicals onto that column and we measure the retention volume as in any other gas chromatographic application. But we all know that the retention volume from a column depends on the partition coefficient between the mobile phase and the stationary phase. Well, here in our case, our stationary phase is our XAD, our mobile phase is the gas, and so from that we can calculate what the sorption coefficient between the XAD and the gas phase is. The nice thing about a technique such as IGC is that the measurement is relatively fast. And so you can measure sorption coefficients for a very large number of chemicals at a number of conditions. And so what we managed to do is measure 290 separate sorption coefficients, which is for 52 different organic chemicals at a whole bunch of different temperatures between 40 and 100 degrees Celsius, as well as at a range of relative humidities between 0 and 90%. And so the other advantage of doing that with a gas chromatograph is that you can use the oven of your gas chromatograph to control the temperature of your column and therefore also the temperature of your measurements. Now this work is just recently being published in a paper in atmospheric environment. Now one of the advantages of having measured sorption coefficients for so many different chemicals, 52 in all, and by making sure that these 52 chemicals are very varied in terms of their functional groups, so we make sure there are polar chemicals, non-polar chemicals, chemicals with hydroxyl groups, chemicals with halogens, chemicals with carbonyl groups, is that we can do then a multiple linear regression on our experimental data and come up with a predictive equation. And so in this case we predict our retention volume, but this retention volume is directly related to our sorbent air partition coefficient, simply by multiplying it with the density of our sorbent material. And with this equation then, we have the opportunity to predict what that sorbent air partition coefficient is for essentially any other neutral organic chemical. Because we made these measurements at a whole bunch of different temperatures, we can similarly come up with an equation to predict the enthalpy of sorption, which is really nothing but a parameter that describes the temperature dependence of our sorption coefficient. So combined with the equation, we can now predict the sorptive capacity of our XAD sampler for any organic chemical at any environmentally relevant temperature. Now these equations, just for those who might be interested, are called polyparameter linear free energy relationships. And the parameters that we now need to know for our chemicals are the A here, which is the hydrogen bond acidity, the L16, which is the hexadecane air partition coefficient, and a parameter E, which represents the excess molar refraction. And so you may say, well, how much does this help me in predicting things if I don't know what these numbers are? Well, it turns out for many, many chemicals, these numbers are available, tabulated, and even for chemicals for which you don't know what these numbers are, there are fragment-based prediction techniques. So in other words, you really, with the help of these equations, can predict any partition coefficient at any temperature you want. Now, the nice thing is that somebody else, in particular Kai-Uwe Goss, made similar measurements using the very same technique, inverse gas chromatography, for polyurethane foam. So in other words, for the two most frequently used sorbent materials in passive sampler, that is polyurethane foam and XAD resin, we have predictive techniques that allow us to predict the sorptive capacity at a different number of temperatures. So what it also allows us is to compare the sorptive capacity of polyurethane foam and XAD resin. So on the x-axis here, we plot our sorption coefficient to XAD at 20 degrees against, on the y-axis, our sorption coefficient to polyurethane foam at 20 degrees. Anything that falls onto the diagonal line would suggest this is a chemical that has an equal sorption to puff as it does to XAD. Anything that is below has a sorption to XAD that is higher than to polyurethane foam, and anything that is above the line will sorb stronger to polyurethane foam than for XAD. Now what's really important here is the bottom left part of the diagram, because this is where low KSA compounds are. And so in this particular case, it is actually these chemicals where it's important that a sorption material has a higher capacity, because the chemicals up here, they will never reach equilibrium with a sampler anyway, because they have such a high sorption capacity. I mean, look at this. 10, a log scale, this means this is a sorption coefficient 10 to the power of 10. So in other words, the sorbent material has a capacity that is 10 orders of magnitude higher than that of the atmospheric gas phase. And so some of you may have worked with polyurethane foam and XAD before, and you may actually have used single parameter linear free energy relationships in order to predict absorption to polyurethane foam or XAD. So there's the work by Shoaib and Harmer, and there's work by Pankow for predicting sorption to XAD from vapor pressure. The problem with single parameter linear free energy relationship is that they are not generally applicable, that they have a limited applicability domain, because not one single parameter could possibly describe the variability in sorption to something like polyurethane foam or XAD. And so these prediction techniques should only be used for extremely nonpolar substances, substances that don't have any polar functional groups. Now what we did here now is we used our information on the sorption capacity of polyurethane foam and XAD in combination with information of how much XAD and polyurethane foam is in a typical passive sampler. And a typical passive sampler based on XAD would have 10 grams of XAD. A typical polyurethane foam disc sampler would have about 4.4 grams of polyurethane foam. And we calculated for pesticides, polychlorinated biphenyls, and different PAHs, the time it would take for a passive sampler to reach 25% of equilibrium. And so that time essentially is what we call the linear uptake region. So this is how long you could operate your passive sampler without it leaving the linear uptake range. And we also calculated the time it takes to reach 95% of equilibrium. So that is approximately the time that it will take to reach equilibrium. Now every chemical is here represented by a line. And it is represented by a line because the sorptive capacity, and therefore the time to equilibrium and the time in the linear uptake phase depends on temperature. So any lower left of one of these lines represents the temperature 30 degrees or 25 degrees, a high temperature. And anything at the upper right represents a low temperature. So in other words, then we also put these thresholds in there, which are typical time periods that a passive sampler may be deployed. For example, typical puff disk samplers may be deployed between 10 days and 3 months. An XAD sampler may often be deployed between about 100 days and 1,000, in other words, several years. So any line here representing a chemical falling below or to the left of one of these lines would indicate that the sampler is not suitable for these types of chemicals because they would not remain in the linear uptake range. And so what we can, for example, see is here that a whole bunch of lighter PCBs, like the mono di and tri PCBs, would actually reach leave the linear uptake phase of the puff disk sampler already well before 10 days. So in other words, a puff disk sampler is unsuitable for quantitatively sampling the small PCBs. On the other hand, if you leave XAD sampler out there for for 100 days, that is also true for the very light PCBs. But in generally, what you can see is that you can leave an XAD sampler out there for much, much longer than a puff disk sampler as a result of that higher uptake capacity, in particularly for the more volatile chemicals. So to sum up the talk so far, we now have quantitative prediction tools that allow us to estimate the uptake capacity of puff disk and XAD-based passive sampler, and therefore we can estimate the length of the linear uptake region and the time to equilibrium under different temperature conditions. We also know now that the uptake capacity of XAD is considerably higher than that of polyurethane foam for most organic chemicals of interest. So this also means that it allows us much longer deployment times, often in excess of a year for an XAD sampler, whereas a puff disk sampler really shouldn't be used for deployments longer than a few months. I should also mention this is only what determines the maximum deployment period. Of course, the minimum deployment period depends on a number of other things. It will depend on the detection limit of your analytical technique that you're using. It depends on the blank levels that you can achieve in your sorbent material, and to some extent it also depends on your sampling rate. Now the sampling rates for the puff disk samplers are slightly higher by about a factor of 2 to 3 than the sampling rates for an XAD sampler. And for that reason people think that you have to use an XAD sampler for a very long period of time. But of course it's a misconception. You can, just as you can use a puff disk sampler for a month, you can use an XAD sampler for a month. And as long as your detection limit is about a factor of 2 to 3 lower than the one you have for a puff disk sampler, you actually have the same sensitivity and the same capability even at a short deployment period. Now let's switch from the capacity of the sampler to the kinetics of the sampler. Now we get to the point where we talk about how fast the uptake is. We get to the point, what is the slope of our linear uptake phase? And what we typically do is, in order to get these numbers, is that we design a calibration study. And a typical design of a calibration study is that we take out a whole number of passive samplers and we deploy them in the field at the same time. And then at regular intervals, we take some of them back into the lab. So some of them are out there for a month, some of them for 2 months, others for 3, 4, and so on, possibly up to a year. We determine in each case how much amount is sequestered, our delta M, and then we can plot the delta M against the time of deployment. And so we, in other words, we measure one of these uptake curves. In order to get our R, we of course need then information on what the air concentration is. In other words, we need to make independent measurements of the air concentration using one of the established techniques that rely on a pumped sampler, a high volume or a low volume pumped sampler. And then we can derive our sampling rate R from the slope of these uptake curves. Now, one of the issues with these approaches is that many of the established techniques for air sampling semi-volatile chemicals are really not designed to collect air for very long periods of time, certainly not to collect over periods of months to a year. So what actually many calibration studies do is they have episodic sampling. So your passive sampler may use sample for a whole month or for 2 months, but you only take a high volume sample every week, because otherwise you would end up with a huge number of samples. The other problem, of course, is that during your 1 month, 2 months, 1 year deployment, your air concentration, of course, will not be constant. But you can take this into account. So, for example, I come from a very seasonal climate, and so air concentrations of pesticides are also very seasonal, because in Canada nobody uses pesticides in the winter, because you wouldn't apply your pesticides on a layer of snow. So your air concentrations also have very seasonal pattern with much higher concentrations in the summer. So if you happen to start your calibration study in the winter, what you would actually get is an uptake curve that looks like this. In the initial months of deployment, when it's still winter, very low concentration, so you take up very little chemical. Then comes the summer, and the concentrations go up, and so the amount sequestered in your sampler also goes up very quickly. And then it becomes fall and winter again. The farmers don't use pesticides anymore, concentrations goes down, and therefore also the collection of chemical in the sampler goes down. Of course, what we do in the winter in Canada, we heat, and we heat with fossil fuels, and so we emit PAHs in the air. And so the air concentration seasonality for PAHs is just the opposite of that. The pesticides, we have higher levels of PAH in the winter, and so the uptake curve would also look different. And of course, the uptake curve would also look different if you started in the summer, your calibration study, rather than in the winter. Now, this would be the results that you get from a calibration study. So here, these would be your air concentrations as a function of time as determined by a classical technique. In this case, we used a low volume sampler. So over a whole year, we took low volume samples every 2 weeks for a 2-week period. And so you see in the winter, we have higher levels of pyrene, one of these PAHs. On the right-hand side, you have that uptake rate. And so this is the sequestered amount against the deployment length. And so indeed, in the winter here, we first have a relatively fast increase in the sequestered amount. Over the summer, nothing much happens. And then as it gets winter again, the sequestered amount goes up again. So in order to now use this for calibration, we have to linearize our data. So instead of simply using time here, we weigh our time by the concentration that actually prevailed during the time of deployment. And so our nonlinear uptake curve becomes a linear uptake curve. And then we can use 2 different ways of calculating an uptake rate from this. One would be to do a least square regression on all of the data at the same time. Or we take simply the slope of each individual sampler, depending on how long they were out there, and then we average these various slopes. But more or less, we get more or less the same result. And so what we actually see here for pyrene, all of our sampling rates, no matter how long our sampler was out there, is more or less the same, which is what we would hope for. But we also have other cases. This is, for example, the uptake curve of naphthalene. And naphthalene is a much more volatile chemical than pyrene. And so what we see is an uptake curve that goes up relatively quickly, and then it becomes shallow. In other words, the sequestered amounts in the later part of the calibration were much lower. And when we then plot our data in a linearized fashion, they still don't become linear. So in other words, what we have indication here is that our naphthalene reached equilibrium with our sampling material, XAD in this case, within a relatively short time period. So naphthalene essentially equilibrates with XAD in a time period of about 2 months, and you really shouldn't take an air sampler that was in the field for a year in order to report naphthalene concentrations. Now this is a chemical that at first sight has a very similar uptake curve to our naphthalene, a relatively steep initial increase and then nice shallowing off. So we would be tempted to believe that endosulfan may actually also achieve equilibrium with our sampler. But it turns out, of course, endosulfan concentrations are high in the summer, and this is the real reason for this increase. The reason that it's shallowing off here is simply because the endosulfan concentration in the winter are then very low. So when we linearize our plot for endosulfan by weighing time by the air concentration that actually prevailed during the sampling period, we see that endosulfan did not reach equilibrium with our XAD even over a 1-year time period. Now, it turns out we can actually use a third way of deriving a sampling rate from one of these curves. And that is to always look at the difference in the sequestered amount between two sequentially retrieved samplers. So for example, we have a sampler that came into the lab after 4 months and one that came back after 2 months. And we can look at the difference between these two samplers in the sequestered amount, and then we compare that to the air concentration prevailing during these 2 months. And so really what we look at is for each individual interval, in our case for each individual 2 months period, we get a sampling rate. And so we did this in the case of hexachlorobenzene. And so what we actually noticed there is that there are slight variations in the sampling rate depending on the season. And in particular, we found out that the sampling rates in the summer are higher than the sampling rates in the winter. So we had indication that our sampling rates are somewhat temperature dependent. So our hexachlorobenzene is taken up slightly faster when it's warmer than when it's colder. At this point, it didn't really come as a surprise to us, because over the years we had been doing a number of calibration studies, and we had done them under different temperature conditions. Our first study was actually in the Arctic and in the Great Lakes region. It was the first time we calibrated our sampler. But since we have also worked in the humid tropics, we did a calibration study in Costa Rica. We also did one in the arid subtropics in Botswana. And more recently, I showed you that the data just in the previous few slides. They were for another calibration study in southern Ontario. So in other words, we did studies under different climate and therefore temperature conditions. And indeed what we found was that the sampling rates tend to be higher in tropical areas than they are in temperate areas. And in temperate areas, they tend to be higher than in Arctic areas. So in other words, we found out that there is a clear temperature dependence of our sampling rates, and it's the same temperature dependence that we found from our seasonal variability. When it's warm, our sampling rate is higher than when it's cold. The other thing that we found out from these calibration studies, and that surprised us initially as well, is that these sampling rates are compound specific. So in other words, smaller compounds tend to have a faster uptake than relatively big compounds. And of course, what we also get out of it is the numerical value of these sampling rates. For the XAD sampler, they are between 0.5 and about 5 cubic meters a day. So what we really learned from all these calibration studies is that one really should use compound and site-specific sampling rates in order to convert sequestered amounts into air concentrations. Now, very often we don't necessarily have information on compound and site-specific sampling rates. And so what we actually developed are some decision trees. Depending on what kind of data you have available, how can you get your best type of sampling rates with the information that you have available. So I won't go into this in detail. I'm just going to give you one example. And the example is for our study in Botswana, where we used an approach to get both compound and site-specific sampling rates. One of the requirements for using this technique is that we have at least one substance in our network that has uniform air concentrations throughout the area that is sampled. Now, the nice thing is that there is a compound like this very often, and that is hexachlorobenzene. Hexachlorobenzene has an extremely long atmospheric residence time, well over a year. And so if you're in an area where there are no major sources of hexachlorobenzene, you essentially have uniform air concentration. No matter where you go, you measure the same thing. And we have found this before on a continental scale when we measured all across North America. you more or less had the same hexachlorobenzene concentration whether you measured in downtown Toronto or whether you measured up in the Canadian high Arctic. That certainly was also true across the country of Botswana. In all of our passive samplers, we had about the same amount of hexachlorobenzene being sequestered, which makes sense because we don't expect there to be any sources of hexachlorobenzene within Botswana. So what we can take now is we can take the annual average concentration of HCB that we derived from a high volume campaign. We also measured the concentration at one site in Botswana for an entire year using a pump sampler, and that happened to be 14 picograms per cubic meter. And then for this concentration we assume applies across the country. So no matter where we are in Botswana, we assume that our air concentration for HCB was 14 picograms per cubic meter. And so what this allows us to do is get a site-specific sampling rate for the one compound, which is HCB. For every site in Botswana, we know now what our site-specific sampling rate is. At the same time, we can now look at the ratio in the sampling rates that we had at that one sampling site where we ran a high-volume sampler. So we can calculate a ratio in the sampling rate of one compound relative to the sampling rate of hexachlorobenzene. And then we make the assumption that this ratio is constant across the country. And so with this, then, we can multiply our site-specific sampling rate for HCB with that ratio of sampling rates between another compound and HCB. And so this way, we get a sampling rate that is not only specific for each individual sampler, but also specific for each individual chemical. And therefore, we can have more confidence that our volumetric air concentrations are reliable. So again, to summarize up to this point, we find out that sampling rates differ between chemicals and differ between environmental conditions, in particular temperature, and we also found out with wind speed. But we also have to admit that we still lack a full mechanistic understanding of why that is. But what it really means empirically, we need to use compound and site-specific sampling rates. And one way to achieve that is by normalization to a compound with uniform air concentrations across the entire network, and very often hexachlorobenzene is that compound. I want to stay with the topic of uptake kinetics, but instead of doing empirical studies in the field, we want to now look at mechanistic study in the laboratory, where we actually try to get a better understanding of the factors that control the rate of uptake in passive samplers. Now, let's start with some sort of conceptual understanding. What is actually that mass transfer coefficient that we encountered on our very first slide that controls the rate of uptake of our chemical in our sampling material? And so let's call that mass transfer coefficient K0. And of course, the inverse of a mass transfer coefficient is a resistance. So it's a resistance to uptake. Now, in this case, we assume our sampler is a puff disk sampler. The first thing that the chemical has to do, it has to diffuse from the outside into the housing. And so we have a resistance that is posed by the housing. We have a mass transfer coefficient in air for the housing. Once it is in the housing, it has to diffuse across an atmospheric boundary layer, essentially a stagnant film on top of our polyurethane foam. And so that's again a resistance to uptake. It's the reciprocal of another mass transfer coefficient, this time for the atmospheric boundary layer. Once it is at the boundary layer, it has to diffuse through the pores of our polyurethane foam in order to reach a surface of polyurethane foam. And again, this is diffusion in air, a mass transfer coefficient for diffusion through the air pore space. And finally, our chemical now diffuses from the surface of the polyurethane foam inside the polyurethane itself. And we may describe that with the help of another resistance term, 1 over Ks, but this time, because the diffusion is not in air, but it is in the sorbent material, we have to include here the sorbent air partition coefficient. So that's the same one that we encountered in the part of the talk that dealt with the uptake capacity. And so, in other words, we have three steps in the uptake that rely on diffusion through the airspace, and one of the resistances that relies on diffusion through the sampler material. Now, what are the current models of uptake in polyurethane foam disk samplers? Well, normally people make a number of assumptions. The first assumption is that the concentration outside and inside the housing is the same, which really amounts to the assumption that the KAH is a very large number and the resistance that is posed by the housing is a very small one. The next assumption that is normally made is that our chemical adopts a uniform distribution within our polyurethane foam. And this assumption really amounts to the same as saying that our chemical has not to diffuse through pore space, because it's automatically, immediately, uniformly distributed. So even if people who use that model don't necessarily know about this, they also make the assumption that the diffusion through the pore space does not pose a resistance. And finally, we already know that we apply our technique to chemicals that have very high sorbent air partition coefficients, because then we are remaining in our linear uptake phase. If KSA is very large, our term 1 over KSA of course becomes also very small. So in other words, we reduced our relatively complex mass transfer term to a single mass transfer term, which describes the diffusion across the boundary layer on top of our polyurethane foam disk. And so this is what most people assume, that the uptake in a passive sampler is simply be governed by diffusion across the boundary layer, and therefore as the ratio between the diffusivity in air and the thickness of that boundary layer. Now, we know a lot about the diffusivity of a chemical in air. And so if our sampling rate is proportional to the diffusivity in air, in principle we should know a lot about the sampling rate. So for example, there are people that look at predicting diffusivities in air from temperature and molecular size. And so that's a rather complicated equation, but essentially all you need to know is if you know the molecular size of your molecule and your temperature of your molecule, you can use that equation to calculate what your diffusivity is. And of course you could then do that for different chemicals and compare the diffusivity. You can do that at different temperatures and compare the diffusivities at different temperatures. So in principle you should be able to use this equation to say something about the compound specificity of your sampling rate and about the temperature dependence of your sampling rate. While the unfortunate thing is that the variation of the sampling rates for different chemicals is much, much larger than we can explain by the effect of sampling of molecular size on diffusivity. So in other words, hexachlorobenzene and an endosulfan molecule should diffuse more or less the same way, maybe 1.3, 1.5 times different, but in fact they diffuse 3 times different. So in other words, we cannot explain why the compound specificity is so strong as it is. The same is true with our temperature dependence. Our sampling rates in the Arctic are about a factor of 4 lower than our sampling rates in the Arctic, in the tropics, but our diffusivities are not different by a factor of 4. So in other words, we have a difficulty in that our empirical information on compound specificity of sampling rates and temperature dependence of sampling rates does not mesh with our theoretical understanding of sampling. And this incidentally is of course not just true for XAD samplers, but it's also true for polyurethane foam samplers, because others like Harrod et al. And Klanova et al. Have shown that puff-puff sampling rates are compound specific and are dependent on temperature. So really we have to conclude that our current understanding of uptake in passive air samplers is incomplete at best. So this brings us to our efforts to try to understand this process in more mechanistic detail. Now one of the nice things about the XAD sampler is that we can use our sampler and replace our XAD with silica gel that we dried first. And instead of measuring the uptake of volatile organic chemicals in XAD, we measure the uptake of water in silica gel. So why is that advantageous? Well, we can replace a Soxhlet extraction and a GCMS analysis with a analytical balance, because we can simply weigh. That's what we do. We place our sampler, which in this case has now silica gel in it, under a table, and we hang it on an analytical balance, and we simply record the increase in the weight of that sampler over time. The other big advantage, of course, is if you do an experiment with uptake of organic chemical in XAD, you have to do this over months to possibly a year. So in other words, it is a very long experiment. Well, if you measure the uptake of water in silica gel, your measurement is done in 10 minutes. So in other words, you can do many, many, many more measurements than you otherwise would be able to do. And so, for example, one of the things we studied is what is the impact of the sampler configuration of the sampling rate. And so for our sampler, we have a long version where our tube here is about 20 centimeters long, and we have a short version where the tube is half that long, 10 centimeters long. And we also took the long one, but instead of fulfilling the entire cylinder with XAD, we had a rod in the middle. So the XAD was actually only in a cylindrical shape, and the center of the sampler was taken up by that rod. And then we use that water uptake technique to measure what the uptake rate is. What we find out that these two configurations gave us the same uptake rate, and this configuration gave us about half that uptake rate. And when we normalized our uptake rate by the surface area that our sampler exposes to the atmosphere, we actually end up with more or less the same sampling rates. So one of the things we learned from this is that our uptake rate is directly proportional to the surface area of our sampler. That's important because it really means we're wasting XAD if we use a sampler like this. XAD is expensive. In fact, it's the most expensive part of our sampler. So if we use this type of design, we don't lose anything in terms of our uptake kinetics or how much our sampler will take up, but we can save half of the XAD that we actually have to purchase and use. Another thing that we want to know, sometimes our sampler become unhooked during a one-year deployment, and then the sampler may be at slightly different height within our housing, and we wanted to know whether there's a difference. It turns out there is not. We don't have to worry about that. But we still wanted to know how important it is where in our housing our sampler is located. So we took one of the short cylinders and put it in a long housing, but at different elevations. And it turns out that we found significantly different uptake rates. So in other words, the bottom part of the sampler will sample more than the top of the sampler. So in other words, there must be some differences in the uptake within our sampler housing at the top and at the bottom. Now again, this is not unique to the XAD sampler. And again, it's a study by Harrod where they found out, if they did a study where the polyurethane foam disc was located a little bit higher within their housing, they got significantly different sampling rates. I mean, they did this because they wanted to put something else into their housing here. So, but in other words, simply the location of your sampling material within your housing will affect your sampling rate. And it is true for the puff disc sampler as well as the XAD sampler. However, this technique that relies on the water uptake in silica gel has also its limitations. For example, we thought we would get a handle on the temperature dependence of the uptake rate. So we took our balance with our sampler and the silica gel uptake rate into environmental growth chambers, and we measured the uptake at temperatures between about 5 and 40 degrees. And what we found out is that our uptake rate for water in silica gel actually became slower as it got warmer. So it was the opposite actually what we observed with our organic chemicals. So in other words, that water uptake model is only suitable for certain aspects of the uptake, understanding the passive samplers, but it's not suitable for understanding others. We, of course, did also experiments not only with water uptake in silicate shell, but also with organic contaminant uptake in samplers themselves. And this time, we went to 4 indoor locations, and we split our sampler into 3 axially segmented parts. And so this way, we were able to actually analyze each of these sections separately. So we could find out whether our bottom of the sampler has a different uptake rate than the top of the sampler. And so this is a bit of a complicated diagram here, but here on the x-axis we have different PCB congeners. And the line here represents the amount that we sequestered in one of the long samplers. In other words, a sampler that was not divided into 3 sections. And then the blue, the red, and the green represents the amount that was in each of the individual sections. So the first thing we can say is that the sum of the amount in the 3 sections corresponded exactly to the amount that was in the sampler. So it's really just a quality control issue, which is great. But the other one is that if you look carefully, the blue bars are always longer than the red bars, and the red bars are longer than the green bars. So in other words, we confirm what we found with our water uptake experiments, that whatever is lower in the housing has a higher uptake rate than what is at the top of the housing. Now, this is now the plotting how much was in the bottom part, middle part, and top part. And so first we thought maybe there are differences between different chemicals. Remember, we want to actually find out why there is compound specificity in our uptake rate. But in fact, if you normalize it, all of the PCB congeners exactly had the same relative distribution between top, bottom, and middle. So in other words, even so, we have a difference in the uptake rate at the top and the bottom. It cannot serve to explain why we have compound specificity in our uptake rates. So the effect is the same for all congeners. Another thing we did was we did a sample where we had the segmented sampler, but in this case we blew wind into it. And so what we found out is that the uptake rate, of course, goes up tremendously. So this is the sequestered amount without wind, the sequestered amount with wind. The blue one is comparing what was in the bottom part. The red and the green is comparing what is in the top and the middle part. So what it really means, the uptake rate in the bottom part went up by a factor of 4. The uptake in the top and the middle part went up by a factor of 6. A result of this is that now our 3 sections here have exactly the same amount, more or less. Whereas without wind, our bottom section had more than the top section. So really, it makes sense if you have turbulence induced within our sampler. Now the resistance to uptake is the same whether you are in the top of the sampler or the bottom of the sampler. Now, an experiment that we also undertook, now first we looked at the radial segmentation, but we want axial segmentation, but now we also wanted to know the radial segmentation. So we made another version of our sampler, which consists of 3 concentric cylinders, all made up of the same mesh. And each of them we fill separately with XAD. And so after exposure, we can take them apart, and we can analyze each of the layers separately. We did the same thing with polyurethane foam, in that we didn't use a disc, but we used a plug. But we cut that plug apart into layers about 1 centimeter thick, and then we can assemble our puff discs or puff plug, expose it, and then before we analyze it, we take it apart into the constituent layers again. And so this is what this looks like. So here we have the 3 concentric tubes where we can fill in XAD, and these are the various layers of our polyurethane foam plug, which we then can reassemble in order to expose it. And so we did calibration experiments indoors for about half a year with each of these. And some of these are not really analyzed yet, but these are some early results. Now this is from the polyurethane foam sampler. And so what we see here is, again, as a function of deployment time, the sequestered amount. And so we have a nice linear uptake, in this case, for a pentachlorobiphenyl. But what I should also say is what's green here is the amount of chemical that is on the outside layer. It's on the first 1 centimeter of puff disk on the outside of the disk. And you see also that the inner layer, middle layer here, doesn't even figure here. So in other words, even after 12 weeks of exposure, there was no pentachlorobiphenyl that moved more than a centimeter into the puff disk. Now this is a very volatile PCB, PCB1, a monochlorobiphenyl. And so here, after about 4 to 8 weeks, we had some progression of the chemical into the inner layers. But it actually took, again, about 3 months before we even measured the lightest PCB congener on the inside of our polyurethane foam. So in other words, the assumption that we make in our uptake model of a uniform distribution of our chemical within our polyurethane foam or XAD is certainly not valid. And so in other words, the model that is commonly used to interpret passive air sampling rates is not valid either. So highly non-uniform distribution of organic compounds within the passive sampling media really invalidates the existing models to interpret the kinetic in passive samplers. But it may also be the key towards understanding the temperature and the compound specificity of our sampling rates. And I should also say it puts into question the use of depuration compounds that are very popular with polyurethane foam disk samplers, because of course the depuration compound theory also depends on uniform distribution of your depuration compound within the sampler, which certainly is not the case. Or if it is the case, it is not applicable to your uptake where your chemicals do not become uniformly distributed. So I haven't actually talked about what you can do with them. So we did a number of studies evaluating the performance of the sampler. In other words, we compared it with established techniques. But it's sort of boring, so I'm not going to talk about it. Suffice it to say that the agreement is not perfect, but we're talking about agreement within a factor of about 2 to 3. Also, we find out that the agreement gets better the longer the averaging time. So in other words, if we compare annual averages, we get a very good agreement. If we compare averages on a sample-by-sample basis, we normally don't get such a nice agreement. Now, for this talk, I assembled all the studies that we have been doing with our passive sampling. I was a little shocked how many we did. But essentially, the advantage of passive sampling networks is that you can operate them on any scale. And from the global scale all the way to a very local scale where you look at concentration distribution on the scale of meters if you want to. And so in other words, in each case you can have networks. And of course, you will have differences in the type of information that you will get at different levels. However, by having done studies at multiple scales, what we can actually do is compare the concentration variability from networks at different scales. So one of the things we did, we have a North American network, a global network, and networks in Costa Rica and Western Canada. So in other words, we have nested network. North America is obviously part of the globe, and Western Canada is part of North America. So the blue diagrams here, they represent different years of our global network. The light blue represents our North American network. The pink one here is the Costa Rican network, and the yellow one is the Western Canadian network. So what you really should take away from this is the smaller the scale of your network, the smaller the concentration variability becomes, which of course makes sense. If you work in a relatively small area, you have a smaller variability in the concentrations. So in general, North America has less variability than a global network. a Western Canadian network has less variability than a North American network. However, we also found out that Costa Rica had, for example, very often a similar, if not a higher concentration variability than the whole North American network. Well, that had to do with the type of network it was. The North American network was essentially restricted to remote areas. The Costa Rican network included cities, agricultural areas, remote areas, and so the concentration variability does not only depend on the scale of the network, but it also depends on the variability of the type of sites that you have within your network. The main piece of information you get out of a passive sampler network is spatial variability. And that is again true on the global scale, it is true on a regional scale, and it is on a local scale. And again, I can't go into detail here, but for example, in the global network, compared different world regions, Europe versus Asia, versus the South, versus North America. However, what's also interesting is that you can use passive sampling network data for temporal trend analysis. And in our global network, we actually had now 4 years of data, and it turns out that many of the temporal trends that we could derive were indeed statistically significant, even so it was only 4 data. Now, anybody who has worked with air data and tried to determine statistically significant trend data will tell you you can never do this with 4 air samples. But of course, what these people use are high-volume air samplers, where you may take a sample every 12 days or whatever for 24 hours. The advantage of a passive sampler is, if you leave them out for a whole year, you actually get a time-integrated measurement for the whole year. You sample every single minute of that year. And so you don't have that very large noise in the data that you get with high-volume samples. So in other words, a passive air sampling approach is actually more powerful when your only interest is in interannual time trends, because then you can get the same information with much, much less information. In other words, with a single sample per year, you can get significant trends over a time period of about 4 or 5 years. Another big advantage. The biggest problem with passive air samplers is that uncertainty in your sampling rate, because it's compound specific, it's temperature specific, and that so on. Well, that doesn't matter if you use a passive sampler for for time dependence, as long as you deploy your sampler always at the same place. Because all of the factors that will contribute to sampling rate variability, temperature, wind speed, and so on, more or less they are the same from one year to the other. So in other words, as long as you sample at the same place, you don't even need a sampling rate. You can simply compare your sequestered amount from one year to the next, and you circumvent the use of sampling rates altogether. So to summarize, passive air samplers are well suited to map spatial variability. Spatial variability is spatial variability in air concentrations, I should say, is always indicative of sources. So in other words, you can use a passive air sampling network to identify where sources are, on a global scale, on a regional scale, and on a local scale. You can use passive samplers for long-term interannual time trend monitoring, and they're probably better suited than the traditional high-volume samplers. Because of that, passive samplers are really ideally suited to monitor compliance with bans, because essentially they give you an idea of where and when chemical is used. However, if you have a very large-scale network, for example, a global network, the number of site types that you have in your network should be limited. Otherwise, you really need to have a very, very large number of samples in order to capture the entire concentration variability. And I want to conclude with really mentioning and acknowledging the 3 people that did all the work I'm talking about. Jeannie and Steve defended their PhD thesis a month ago, and Xianming is still on it. But these are actually the people that did the work.